proving the converse. The converse is not always true, right? But the converse means that if P implies Q is my statement, then the converse of that is Q implies P. This does not always lead to a truth. We learn that with if I am in Paris, then I am in France. That's a true statement. But if I am in France, then I am in Paris is not a true statement. So prove that the converse of problem 1 is true. So problem 1 that we had was if x squared equals 9, then x equals plus or minus 3. And to prove that converse, all we need to do is, once again, start off with our statement and rewrite the converse. So the converse switches the conclusion and the premise, and that would be if x equals plus or minus 3. And let me write it out like this. If x equals 3 or x equals minus 3, because that's what plus or minus means, then x squared equals 9. Now in this case, this statement is going to be true, and it's not terribly difficult to see, because if x is 3, then 3 squared is 9. If x is negative 3, then negative 3 squared is 9. So all we're doing when we're trying to establish whether a converse is true is rearranging our two terms, and now our premise becomes Q, and we want to walk ourselves in a series of logical steps to show that this conclusion follows. So suppose, as a proof, suppose x equals 3 or x equals minus 3. And this is going to be a really quick one. In either case, when x is 3, 3 squared is 9. So that's a check. And negative 3 squared is 9. And that's a check. Therefore, whether x is 3 or x is negative 3, the square of x will be 9. And so this is no different in logic than our previous two proofs for even and odd numbers. The only difference is here that we're taking a statement that was of the form P then Q, and we basically wanted to say, well, if you flip the conclusion and make that the premise, will that lead to the thing that used to be the premise? And in this case, it does. So because it works both ways, because P implies Q and Q implies P are true statements, we write P if and only if Q, and say P if and only if Q. This is called a biconditional statement. It is true in both circumstances. Now, probably one of my favorite ones when I was going to school was disproving a statement. And disproving something is often easier than proving something is true, because to disprove something, first of all, in Boolean logic, a statement is either always true or it is not always true. So that means if something is not always true, it is false. And that is sometimes a hard pill to swallow, that even if you find just one exception to your rule, that makes that whole statement false. To show something is false, we only need to come up with one example of where the statement fails. This then disproves the truth of the statement. So this is called a counterexample, an example that counters the argument, and show by coming up with a counterexample that the converse of the following statement is false. Excuse me, that the following statement is false, not the converse of, that the following statement is false. So if x is an element of A intersect B, then x is an element of A. Okay, so that means, oh no, I'm sorry, we do want the converse of that. We'll practice the converse of the following statement. So if x is an element of, as inside of the intersection of A and B, you can agree that x is an element of A, right? Because it's inside of A and simultaneously part of B as well. But to prove the converse of this, well, let's think about what the converse would be. Here I have the statement, if P, then Q. So if I want to write the statement Q, then P, that would be if x is an element of A, then X is an element of A and B. And we want to show this is false. Okay, so we just need to find one counterexample. Here we're arguing that for any element that is in some set called A, that it's also in the intersection. So I'm going to try to think of an example. Well, first of all, I can just visualize this and start thinking about what would happen if I had two sets, A and B. And in that set, if I had, or in that universe rather, I had these two sets, A and B. So I'm starting to think about this. What's going through my mind? Well, I know I have A and B, and there's going to be some intersection possibly here. So let's say I have an element inside of A. Is it guaranteed that just because it's inside of A, it's also inside of B? Well, no, because I can pick an element here, or even here, or even here, and all of these points are in, that dot is in A, and it's not in B. So it doesn't necessarily guarantee that X being an element of A is also an element of B simultaneously. All right, so let's actually formulate a more robust, so you could use this argument as long as you use some words, like you could say, as long as the viewer could see this and say, well, here's an example, the elements above in A above are not in B. And so that's the counterexample that we could give. Another counterexample that you might be able to give is a numerical one. So you could say something like, suppose A is equal to the set, we'll say 1, 2, 3, and we'll say B is the set 3, 4, 5. So notice that 1 is an element of A, but 1 is not an element of B. Therefore, not all X in A, not all X in A are also in B. And that's a counterexample. So somebody made the claim, but we just said, nope, your claim is false. I just found an example, or at least one example where your statement is false.